In the last class, we have read how to design the different type of adders, mainly the half adders, the full adders, and the different type of realization using a variety of gates. Today we will see how we can design the subtractor circuits. Now, a half subtractor is a combination circuit that subtracts 2 bits and produces their difference. It has also an output to specify if a 1 has been borrowed. So, the similarity with the adder is that in case of addition, it was for addition it was the carry signal. For addition, one sum and one carry has been generated. For subtraction, that sum is replaced by the difference because it computes the difference, and the carry, here the carry concept is actually the borrow. So, we denote this as a B and the difference as D. Now, how the operator operates on the 2 operands. So, again first we see the addition operation. See here that 0 plus 0 equal to 0 and the carry is 0. 0 plus 1 is 1, carry is 0. 1 plus 0 is 1, carry 0. 1 plus 1 is actually 1 0. So, sum is 0 and carry is 1. Now, see if I want to change this operation addition as subtraction, then what we can do, this 0 plus 0 equal to 0. So, as if one operand from here, say this 0, I can shift here. That means, say if I want to shift this 0 here, means this will be 0 minus 0. So, what will happen, say for this addition, if this plus 0 shifts on the right side, then it becomes minus 0 and the left hand side will be the result. That means, this is a 0. So, that thing we have expressed in the right side. So, now for the same combination of the 2 operands, what we have done, that 0 plus 0 is 0. So, 0 minus 0 is 0. Again 0 plus 1 is 1. So, here we can tell this thing that 1 minus 1 is 0. Similarly, 1 plus 0 is 1, that means 1 minus 0 is 1, and 1 plus 1 is 1 0, means the sum is 0. So, sum is 0. So, 0 minus 1. So, this plus 1 will go here, that will be minus 1. So, that has been written here 0 minus 1 and the result will be this one. So, 0 minus 1, this one. Now, what happens with this carry? What is the effect of this carry? So, as if 0 from 0 I am subtracting 1, result is also 1, provided that it has borrowed a 1 from the next higher stage. So, 0 minus 1 is 1, borrow 1. So, in this way we can define the subtraction operation from the addition operation itself. So, what we have just now read, if I write in the truth table form, that means AB are the 2 operands, these are the 2 operands, B is the borrow and D is my difference. So, AB are the operands B is borrow and D is the difference that we want to compute. Now, 0 0 borrow is 0, difference is 0, 0 1 0 minus 1, this is the situation that when borrow is 1, difference is 1, 1 minus 0, difference is 1, borrow 0, 1 minus 1, difference is 0, borrow 0. So, now if this truth table we can express the, or we can draw the Carnot map for this, one for B and one for D, then we will get the expression for D and B, and in this way we can get D equal to A dash B plus A B dash, because now we can see, just we can notice that this D value is same as that of our sum of the addition operation. For the sum also it is 0 1 1 0. So, this is already we have seen in the last class that this is nothing but a XOR, 2 input XOR, A dash B plus A B dash. Now, the borrow is 0 1 0 0. So, if we draw the Carnot map, then it will be for the if this is A B 0 1 0 1, then only for 0 1 case, that means A is 0, B is 1, there is only 1 and all are zeros. So, this mean term is A dash B. See here that this is my borrow is A dash B. So, this my borrow is A dash B. So, the half adder or half subtractor circuit, again there will be two output, one for the difference, one for the borrow. As already we have seen, the difference is same as that of the carry of addition operation, that is 2 input XOR, and that is if it is the AND OR realization, then A B dash and this is A dash B, the two input AND gate, and then the output of the AND gate is fed to a 2 input OR gate. So, this gives the difference A B dash plus A dash B, and the borrow is A dash B. So, again it is the 2 input AND gate, only the input is one input is A dash and another input is B. So, this is totally similar with my half adder. So, half adder and half subtractor is almost same, only the expression of borrow differs from the expression of the carry, but the sum and the difference is totally same. Now, design of a full subtractor. So, just like the addition operation or the full adder circuit, now we can define a full subtractor as a combinational circuit that performs the subtraction between two bits. A 1 may have been borrowed by a lower significant stage. So, mainly the half subtractor, for the 2 bit, mainly the subtraction is being done between 2 bits. So, one difference is generated and one borrow is generated, but if it is a n bit subtractor, then this we cannot neglect this borrow. So, this a borrow may have been borrowed by a lower significant stage, means when just like the full adder circuit, say if we take 1 0 1 0 and we want to subtract say 0 1 1 0, then say 0 minus 0 is 0, 1 minus 1 is 0, but 0 minus 1, say here actually 1 0 as if we have borrowed a 1 here, this 0 becomes 1 0. So, 1 0 minus 1 we know from the addition operation this is 1. So, borrowed 1, then this is 1. So, 0 1 0 0. So, if I take the decimal equivalent, we see that 1010 is nothing but 10, this is 110 means 6, and if I take the subtraction then it will be 4, which is nothing but our 0100. See here, this every time here the borrow is nothing has been borrowed for these 2 bits. So, borrow bits are 0 for these 2 bits, borrow bits are these 2, the borrow bits are 0, be 0, but this one, that third one, the borrow is 1. So, this is the concept of the full subtractor, again which is same or similar to our full adder, only the borrow is replaced, or the borrow is replaced by carry, or carry is replaced by borrow, whatever we call. Now, again if the input output relationship, we have seen that here also there are 2 outputs, one is the borrow output and one is the difference. So, now as the borrow is considered, that means here this should be my, this carry, actually this should be my borrow B, and that is why the borrow, because A, B 2 operands we have taken. So, we have written as if this C is my borrow. So, for all possible, now there are 3 inputs. So, what we can draw, see this is my full subtractor circuit, there will be 3 input, one are A, B, the 2 operands, another is borrow denoted by C again, and one is the next borrow generated, another is the difference of these 2 bits. So, this is my full subtractor circuit. Now, for all possible combinations we have written the B and D values. So, first we consider the difference. See that if AB is 0 0, already we know that 0 minus 0 is 0, then see 0 minus 0, but this is borrowed one borrow is there. So, this should be, difference should be a 1. Similarly, 0 minus 1, this should be again, that difference is 1, borrow is 1, because already we have seen that if it is 0 minus 1, as if from the highest stage it is 1 is borrowed, and actually it is 1 0. Now, it is 0 minus 1 and there is one borrow also. So, in here also this is 1 minus 1 actually, this 0 and borrow 1. This is 1 minus 0, simple 1 minus 0, 0, because that from the previous there is no previous borrow. So, this is 1 borrow 0. Again here 1 minus 0 borrow 1. So, that means actually 1 minus 1. So, difference is 0, borrow is 0. Now, 1 minus 1 borrow 0. So, simple, all are zeros, borrow 0 as well as difference 0. Here 1 minus 1, but one borrow is there. So, if it was 0, just the previous case as the borrow is 0. So, 1 minus 1 we know that difference is 0, borrow is 0, but here 1 minus 1, as one borrow is there, previous borrow is there, that is why the difference will be 1 and the borrow will also be 1. So, we can write the output, the input output relationship of the full subtractor. Now, again in the same way we will draw two Carnot maps for two outputs, one for the difference D and another for the borrow B. So, when we write the expression for D, so again if we see that for D there are the number of ones or the min term exist are for 001 means the for decimal 1, then 2, then 4 and then 7. So, 1, 2, 4, 7 the decimal, the min term will be there. Now, see if we draw that there are 3 inputs. So, these are my AB, this is C. So, 0, 0, 1, this is my 1, this is my 1, then this is 0, 1, 0, this is 2, this is 1, 0, 0, 4 and this is 7. So, these 4 min term exist in the expression and these are nothing but A dash B dash C plus A dash B C dash plus A B dash C dash plus A B C, which is same as that of our full adder circuit. Now, what will be the expression for B, the borrow? Again, if we see the borrow, see here for the borrow the min term exists for 001 means 1, then 2, then 3 and for 7. So, min term exists for 1, 2, 3, 7. Now, we see for this is again, if we put this is my 1, 2, 3, 7. So, only these 4 terms. Now, see here then we can form some couple. This will be one couple. For this it will be A dash, it will be A dash B. If we take A B and see it. So, this will be my A dash B. This term has been, this is for this couple. Now, for this couple it will be A dash C. So, for this couple A dash C. Now, for this couple it will be BC. So, this will be BC. So, A dash B plus BC plus A dash C. See, there is similarity between the carry of the full adder circuit and the borrow of the full subtractor circuit. Only the min terms are slightly different. There it was for the full adder, the carry was that carry C was AB plus BC plus CA. So, again that it was a sum of product and there are 3 AND gates are needed and 1 3 input OR gates. Here also the same number of gates are needed, totally similar type of structure or similar type of expression, only here one complemented variable as the input, which is my A dash. Here there is no complemented variable exist. This is the only difference between the full adder and the full subtractor circuit. So, if we see that the full subtractor, the difference for full subtractor, then it is totally same as that of the full adder circuit, because that expression is same. So, already we have discussed this is a 4 3 input AND gate and 1 4 input OR gate is needed. Now, if it is a borrow for full subtractor, then only the inputs are different, otherwise the structure is totally same. For the first gate, for the first AND gate, the inputs are A dash and B, one complemented variable is there. For the second AND gate also one complemented variable A dash is there. For the third one it is only BC and 1 3 input OR gate is needed. So, structure is totally same, only the inputs are one complemented inputs are added. Now, again we see some more about the, or we read some more about the subtractor, because subtraction is more complicated than addition due to the concept of the borrow. Now, we take two numbers, say x and y. See, x minus y we have defined as the difference d. So, d is my difference. Now, what will happen, that if I can write the same expression x minus y equal to d as if x plus y minus d, as if I am, instead of subtracting, I am doing addition, and I am doing addition of a negation of y or the minus y, then it will be same, x plus minus y equal to d. Now, if I would replace x by y, that means if my x equal to y, then this is of y minus y, means the difference should be 0, or if I again arrange, or this expression if I write, this should be y plus of minus y equal to 0. Now, we take a 4-bit y and see that how it works. Say I choose a 4-bit, I choose a 4-bit y. So, these are y3, y2, y1 and y0. Say I am considering another 4-bit w as if w3, w2, w1, w0, where wn is yn bar. So, that means if my yn is 0, wn will be 1. If my yn is 1, wn will be 0. So, now if I take the addition of these two, say y3, y2, y1, y0, and then w3, w1, to w1, w0, then if I take addition, as they are complemented, So, always I will get all 1, because these are always complemented, and 0 plus 1 is 1. Now, I want that y plus of minus y equal to 0. This should be the case. Now, if I add 1, then what will happen? Then only it becomes 0 and a carry 1. So, now if I neglect this carry, or this is a overflow. So, if I drop this one, then my y plus w becomes 0. Now, see, y plus of minus y equal to 0. That means, I want as if this w, I have replaced this w as y complement. So, if I forcefully am making as if y plus minus y equal to 0, then this w is my subtraction. Then what we can call now? See that this all 1, say if I now define in this way, say for 4 bit number, this all 1 is actually 2 to the power. So, this is actually 2 to the power 4 minus 1. So, this is actually 15. So, for in general, if it is a n bit number, then this n number of ones means 2 to the power n minus 1, this will give all ones, all n bit ones, and these 2 to the power n minus 1 we are defining as a ones complement. So, that means that if what we have seen that y plus w, if I take that w is or w n is y n bar, better we take that small w n y n bar, then this is always 1, whatever be the bits. If it is n bit, if it is n bit, then 1. So, this is just the ones complement is the flipping the bits we call. So, we call the flipping the bits, and by flipping the bits it computes the ones complement. That means, say if one number x is 1011, then ones complement of x is 0100. So, that now see 1011 and 0100, this becomes always all 1. So, in this way we define that ones complement. Now, we take the 2's complement also, and normally we define the 2's complement as ones complement plus 1. How? Say the 2's complement of a number, say one number y we have taken, see that 2 to the power n minus y. So, that we can write in this way, that 2 to the power n minus 1 actually minus 1 plus 1 means y plus 1. Now, see 2 to the power n minus 1 already we have defined, this is as a 1's complement. So, 1's complement minus y plus 1. Now, if the overflow is, or this is 1's complement plus 1, 2's complement is, so what we can do, that if now I want to add x, so what will happen, that x minus y will be x plus 2's complement of y, and what we have defined, that 2's complement of y is 1's complement of y plus 1, and the overflow is neglected. So, complementing each bit of y is called the 1's complement, that means the flipping the bits, just now we have discussed. Now, 2's complement of y is obtained by adding 1 to its 1's complement, just now we have seen and we have derived that thing. Then 2's complement y is y plus 1, and y plus 2's complement equal to 0 if the overflow is discarded. So, in this way we will get that x minus y is x plus 2's complement of y. So, this is a very important result, that what we see, that if I want to add or if I want to subtract y from x, that means x minus y. So, there is no separate subtractor is needed if my 2's complement of the number of one number is available. Then what we can do, the same adder circuit can be used for this subtraction. See this x minus y. So, first I will compute the 2's complement of y, and we know that 2's complement of y is the, we will take the 1's complement of y again plus 1. So, this is again 1's complement of y plus 1, this is again some addition, and then it will be added with x. So, no subtraction is there, only the addition circuit is sufficient for subtraction. We take one example first. See, there are two numbers, x is 1101. So, decimal equivalent is 13, and here the decimal equivalent is 5y. So, I want to do x minus y, which should be 13 minus 5 equal to 8, which should be seen. Now, the way we have done, first x minus y should be 1101 plus, see, 1's complement of y means this is 2's complement of y, means first 1's complement of y plus 1. So, 0101 if I flip, then it will be 1010 plus 1. So, this will be 1101 plus 1011. So, this 1 plus 1, or if we add here 1101 and 1011, then 11 0 carry 1, then again 11 0 carry 1, again 110 carry 1. Now, 1110 and 1 carry 1. So, that means this is 1 1. So, one sum is 1 and 1 carry is 1. Now, if we neglect or discard this overflow bit, then it will be 1000, which is the decimal equivalent is 8, and which satisfies our normal results. So, instead of doing the subtraction, actually we have done the addition. So, the simple addition circuit we can easily use for this, provided that 2's complement of that number is available. Now, we take another example. Say x is 1001 and y is all 1. Then compute y minus x when y is of 4 bits and y is of 8 bits. So, first we take the simple one, the y equal to 4 bits. Okay. The same way, here we are computing y minus x, we are computing y minus x. So, y is all 1, x is 1 0 now 2's complement of x. This is equal to 1's complement of x is 0 1 1 0, flipping the bits, plus 1, this is equal to 0 1 1. Now, instead of doing the difference, I will add y minus x is y plus 2's complement of x. So, y is 1 1 1 1 plus 0 1 1 1. If we add, then 1 plus 1 0, this 1 plus 1 0 carry 1. Okay, we are writing here 0 carry 1, 1 plus 1 1 0, So, this is 1, again 1 plus 1, 1 0, and 1 1 1, carry 1, 1 plus 1 0, carry 1. So, this is my overflow bit. I will neglect this one and this should be my 0 1 1 0. So, the result is, if I take the decimal equivalent just to verify whether my difference is correct or not. So, 0 1 1 0 means this is my 6 and y was 15 and x was 9 in decimal. So, 15 minus 9, this is 6 equal to 15 minus 9. So, in this way we will get the result. Now, y is of 8 bits, that means y 1 1 1 1 1, that I can always represent as 8 bit numbers. So, now we see my y is actually 4011, means 8 bit representation. X is as it is 1001. Now, what will happen? Already we have seen that this is y minus x equal to y, and this is 2's complement of x, means this is 0 1 1 0 means 0 1 1 1. Now, if we add, it will be 0 1 1 1 1 0 1 and 0 0. So, what will be the value? See, here it was y was 15, x is 9. Here what is y minus x? Y minus x we have got that this is 0 1 2 4 8, that means 16 plus 4 plus 2. So, 22, this is decimal. See, I have two numbers y equal to 15 and x equal to 9, and when I have taken the difference I got 22, 15 minus 9 is 22. So, this is a incorrect results. Why? What mistake I have done? See, here y is represented as 8 bit and I have taken x as 4 bit. So, this is the incorrect thing. So, I have to take x is also of the same bit size as that of y. So, x should also be of 8 bit numbers. Now, we check whether it gives the correct result or not. Now, y is and x we have taken 8 bit also. Then if I take 2's complement of x then it will be 1 1 1 1, flipping the bits, and this is 1001 means 0 1 1 0. Then it will be plus 1. So, this is 4 1 0 1 1 1. Now, if I do y minus x, so this becomes we have to add this y and 2's complement of x, which is this number 1 1 1 1 0 1 . So, 1 plus 1 0, carry 1, carry 1, again 3 1, carry 1, 1 plus 1 0, carry 1, then 1 plus 1 0, carry 1, 0, carry 1, 0, carry 1, 0, carry 1, overflow, and this is neglected or discarded. Then see, again the value becomes 6 decimal value, and earlier it was 15, y was 15, in decimal, x was 9 in decimal, and the result is correct now. So, this is a correct result. So, what we have seen that if my any one of the number is some n bit number, then the other number should also be of the same size, same bit size, otherwise the result will be wrong. And we have just for this example we have checked this thing. Now, we see that the negative number representation. See, the one thing we know, the sign bit representation for negative numbers, because we are mainly discussing the subtractor, and subtractor we have represented as if this is a addition. So, addition of negative numbers. So, how we can represent the negative numbers? That is one very important thing in this context. Now, sign bit convention of negative numbers, normally we take the MSB as the sign bit. See that if I want to represent say 8, we know the binary of 8 is 1000. If this is a plus 8, so this is a 4 bit representation 8. If it is a plus 8, I am taking another MSB, it is 0 100. If it is a minus 8, this MSB value I am taking a 1 and the remaining as same. So, this is the MSB is represented as a sign bit. So, 0 for plus, 1 for minus, and this is the my MSB bits. So, normally this is the convention for sign bit, and this is a sign bit convention for negative numbers. So, if it is a say 8 bit numbers and the MSB, that means this one, this number is my the sign bit, it represents the sign 1. See, here it is 0, so this is a positive number. Here it is a 0, so this must be a positive number. This is 1, so this is a negative number. This is 1, so this is a negative number. Now see that 0 means if it is a 7-bit representation, all bits will be 0, and MSB is 0, so 0, I am telling this is a positive 0. Why? See, again 1, all 0, this is a negative number, so as if this is a negative 0. For the remaining, so this is one type of confusion, that 0 we know in our number system only 1 in the number axis, it appears only once. Now when I am representing, I am getting two type of representation, one is positive 0, one is negative 0 in sign bit convention. But for the rest of the numbers, it is fine that for up to 0 as 7 bits, for 7 bit we know that it can represent 127. So 0 7 ones means this is a plus 127, and 171 means this is a minus 127. So it can represent minus 127 to plus 127. That means in general, for this is for 8 bit. So for in general, if it is the n bit, then it is for minus 2 to the power n minus 1. See, 127 means minus 1, this is 1 less than 2 to the power 7. So this is minus 2 to the power n minus 1 to plus 2 to the power n minus 1 minus 1. This is a range that one n bit sign, if it is sign bit convention, one n bit number can represent. Now only one drawback of this method is there are two representation of zeros, one we call negative 0 and positive 0. So just now what we have seen that it is a, for this 0, this is a positive 0, this is a negative 0, and this is a drawback of sign bit number. So for this we use the 2's complement representation, which overcomes this drawback. So 2's complement representation, just now we have read that how we can compute 2's complement. Say if it is again, if it is 8 bit, 80 means 0, then 0 to 71 means 127. Now if it is a 1000 means this is a 2's complement number, and this is minus 128. This is a, so see this is minus 128, and 1301 means 000001 means this is a minus 127, and the all 1 means this is a minus 1. So here 0 means only unique representation of 0 is there. So this is valid. This overcomes the problem of the double representation of 0, that confusion it overcomes. So we represent that negative numbers by 2's complement. See here, if I take n number, we take one example that n equal to 100101111, then what will happen? For n equal to, this is minus 128, because this is 0, 1, 2, 3, 4, 5, 6, 7 means 2 to the power this is my 2 to the power 7. So, the first one is the 2 to the power 7, this is minus, and these are plus 2 to the power 4 plus 2 to the power 2 plus 2 to the power 1 plus 2 to the power 0. So, this becomes minus 128 plus 16 plus 4 plus 2 plus 1, and that is minus 105. So, this is my representation. That means, for negative number minus 105 can be represented as 100101111. So, this is the 2's complement representation of negative numbers. So, the subtractor logic circuits we can easily draw that, because it is nothing but that addition only, the 2's complement we have to do. So, if it is a 4 bit number, then only some 4 inverter are needed, because this is for flipping the bits. So, there will be 4 inputs, say this is that x3, x2, x1, x0, that x is the input, then we add, this is plus 1 is added, and it represents the 2's complement of x. Now, one question for quiz question for today's lecture. So, design a 4-bit parallel adder using full adder as its components. So, already we have read the half adder circuit, the full adder circuit, and a variety of full adder, half adder circuits. Now, we will treat this half adder or full adder as if this is the one of the module, just like gates. So, when we have drawn the full adder, we have used the AND OR as the element, digital element. Now, as if the full adder is one module, and then form an 8-bit adder from this 4-bit adder. So, first we have to design a 4-bit parallel adder from the one full adder as the components, then form an 8-bit adder from this 4-bit adder. Okay, thank you.